Finding minimum spanning tree in a connected graph G. We show the graph G by this notation. G is shown by set of vertices V and set of edges E. And spanning tree is going to be a tree which connects all the vertices. Again, the set of vertices is E. And we have set of edges A, where A is going to be sum of vertices from G, so A is a subset of E. And to have subgraph T as a tree, the number of vertices in V, if we name it N, then the number of edges in tree is going to be exactly N minus 1. So tree, by definition, is a connected graph with no cycle, so we will keep in mind that using especially the Kruskal algorithm, we are going to use this one, that we shouldn't have any cycle in the graph. And using the reverse delete algorithm, we should make sure that by deleting the highest edges with the highest cost, we are not going to disconnect the graph. So the graph must remain connected. So it's a connected with no cycle, number of edges n minus 1, number of vertices exactly n. Some other notations that we'll see during the explanation of these three algorithms is this cut. So in the Prim's algorithm, we are going to introduce the cut. In, let's say, ith iteration, we have a set of vertices selected up to this point S. Now I can say that S and S bar, if I show V minus S by S bar, then this set of edges connecting S to S bar, since it's not digraph, so the direction is not important, then we don't show the parentheses. We show the edges inside the curly bracket. So for example here, from S to S bar, so S is the set of selected vertices up to this iteration. We can see that the highlighted vertices A, B, C, and F. We should draw this dashed line that we call it a cut, and these edges are called crossing edges. So among the crossing edges, we are going to find the edge with the minimum Cij or W, whatever name we give for that, and we name it lightest edge. For example, in this case, the set of edges connecting S to S bar are this one, this edge connecting B to E, then this one B to D, and that one C to D, and F to D, F to E, and FG. So these are the crossing edges, and among them we check the Cij's and select the minimum. In this case, we have two edges with the minimum. So we can select either one. For example, here we have F and G, C and D. And I'm going to select in this iteration, for example, CD, and put that one inside the set of edges for tree. So this set of edges in A is going to be increased by 1 in each iteration. And since we need m minus 1 edges, we are going to have a minus 1 iteration for this algorithm for Prim's. Kruskal also is going to be almost the same. In Kruskal algorithm, we are going to add edges one by one, not the vertices. We will find the lightest edge in Kruskal algorithm this time among all the edges. And we will add them to A, keeping in mind that the graph shouldn't have a cycle. So if I have an edge with the lightest, but adding that it may make a cycle. We are not going to add that one. We will skip that and find the next minimum. Reverse delete algorithm. We are going to start to delete some of the edges up until we have exactly n-1 edges and the graph still is connected. So in this case also, if we are deleting the edge with the highest, we should check whether by deleting that edge the graph is going to be a disconnected graph or not. If it disconnects the graph, then we skip that one and find the next maximum and continue up until we have exactly n-1. So for the reverse delete algorithm, we don't know how many extra edges there are there. If we have, for example, like this one, let's say V is, if we have 20 vertices and 22 edges, then it's going to be much better to use the reverse delete algorithm, because in A we have n-1. We need to keep 19 edges. So we don't want to add that 19 edges one by one. Instead, we can remove only 3 edges to get that 19. But we are removing the edges with the highest Cij. Adding, we are doing the same with lowest. And all these three are also called greedy algorithm based on this property of the algorithm. Now we see 2 examples. First, we study this algorithm, Prim's algorithm, on a given graph. The steps of algorithm is going to start like this. This is the given graph. First, we select one of the vertices and put that one inside S. It doesn't matter which one we select, but here I selected A. So the rest of the vertices are inside V minus S. For now, A, the set of edges in our tree, or which is a subtree, not the tree itself. It's not going to be the minimum spanning tree for now until we have exactly n-1 edges inside A. Now, we draw a cut which shows the crossing edges from S to V minus S. So we need to draw this dashed line. I will show how to, this is the line, it's easy, but in other cases I will show some that we need to draw a curve to show the cut and the crossing edges. So in this case we have 2 crossing edges, A to B, A to C. And among them, the lightest is this one. We have one, A to B. So A to B is the lightest. Then we add that one inside A. Now for now, A has only this edge inside. So by this A and B, we mean an edge connecting the vertex A to vertex B. Now in the next iteration, since A to B is selected, we are going to highlight it, and A to B, sorry. And we will highlight B also. So in the next iteration, B also is highlighted. Now A and B are inside S. So we can show like this. This is S. So the arcs going out from this S are going to be the crossing edges. And we can graph a cut also like this. Then we have this 4 edges. 2 of them has the same minimum. This time we have 2 lightest edges. We can select either one, but in this case we are going to have multiple solution. When we finish the algorithm, we will give a multiple solution. So I selected in this case A and C. A and B was inside the set of edges A. Now A and C also has been added. Now since C is inside our subtree, then C will be highlighted, and the edge from A to C also will be highlighted. So we highlighted A to C and also the C itself. Now to show the cut, we need this straight line, and crossing edges are this. The weight for them, or theCijs, are 10, 8, 2, 1. So the lightest is this one. This is connecting C to F. Then we add that C to F inside the A, and the next iteration we will highlight this edge and this vertex. Now this edge and that vertex is highlighted. Now we want to draw the cut. Let me draw this cut one more time. If I want to draw a cut, so I'm going to insert a shape. And we have two different type of curves. This one has only one curvature, but for this one we can turn more than once. So I click somewhere and continue to some point that I want to turn. So I click another here and then turn. If I need to turn any more, I can click one more time. But in this case, I don't need. And when you finish, just press enter and that's all. And go to the shapes and change this, the type for a dashed one, the dashed line. So this is our cut. Now, we don't need that one for now. So I want to show how to draw it. Now, the crossing edges are 1, 2, 3, 4, 5, 6. So these are in the cut. And the lightest, again, we have two of them, C to D and F to G. In this case, we selected C to D and it is inside A. So D is already selected. D will be highlighted. And C to D also will be highlighted. So we will highlight this edge and this vertex. So next iteration, we can see that we have only two vertices remaining to be connected to the rest of the, so we need to have two more edges to connect all the vertices. Now this time the cut is a straight line, crossing edges this 2, 5, 7, 10, minimum is this. So we have only one lightest edge, we add that F and G inside A. And next iteration G will be highlighted, F to G. We highlighted F to G and G. Now this is the new cut. In this cut we have 4 crossing edges with the lightest connecting F to E. So F to E is the lightest. We add that one inside E. Now we can see that now cardinality of A, or the set of edges inside the tree, we have 1, 2, 3, 4, 5, 6. And we knew that the number of vertices is 1, 2, 3, 4, 5, 6, 7. It's exactly n minus 1, so we are done. So in the next iteration, we highlight this edge and that vertex. Now we can remove the remaining. So once all the vertices are highlighted, or if we have exactly n minus 1 edges, then we start to remove this remaining arcs. And we can see that there is no cycle here. This is the final solution, the minimum spanning tree. And the weight for this minimum spanning tree is going to be the sum of the values and the arcs. So you should give all these things as a final solution, which is 22. But we knew that we had another arc here with the same weight. So we can select that one to show the multiple solution, that the problem has multiple solution. This one also is another minimum spanning tree by the same weight. So that's all for Prim's algorithm. Now if I want to continue by Kruskal's algorithm, this time we are starting to find or add edges one by one. So we select the lightest edge among all the edges, and we can see that the lightest is this one. Now originally A is the empty set, S is the empty. If I select this one, then I will add C and F inside A. And since C and F connect C to F, C and F also will be added inside S. Now let's duplicate this slide. So in this iteration, I just highlight this edge and this vertices. Now we have inside A, we have the edge connecting C to F. And inside S, we have the vertices C and F. Now we check the remaining edges and find the lightest. So if I try to find the lightest, we will see that for the next iteration, we have these two edges with the cost 2. So again, we duplicate this slide. Now in this iteration, we can see that I can select this 2 or that 2. If I select this 2 and highlight it, so since this edge is selected, then vertex also must be highlighted. And we can see that in this iteration, what has happened, we added the edge C to F. And since C to D, sorry, C to D. And since D also is now in our subtree, then D will be inside S. So this line will continue up until A has exactly m-1 edges, or for S also the same thing will happen. With S is going to have exactly n vertices. All the vertices are going to be added to S. Now for the next iteration, we do the same. So in this iteration, we are finding the lightest. This time the lightest is this 2. Then I highlight that one. And also the vertex connecting to this. Now here we add one more edge, which is F to G. And G also will be added here. That's it. Now we duplicate this slide again. So in the test, students should show step by step all the process. In each iteration or in each slide, we are adding one edge and one vertex to the subtree up until we get the minimum spanning tree. Now the lightest among the remaining or unselected edges is this 4. Now I highlight 4. So we can see that in this case, we don't need to have A as a subtree because now it's not connected. So A is going to be a part of a tree for now. Now we selected 4, which connects A to B. So we need to highlight A and B. Here we say that we selected the next edge, which is selected as A to B, connecting A and B. And since A and B were not inside S for up to now, we add both A and B. And we duplicate this slide to do the next iteration. So what is the next minimum? Next minimum, we had this 5. So since selecting 5 makes no cycle, so we can select it. I can highlight this and see whether there is a cycle or not. No, there isn't any cycle. Since there is no cycle, we fix it by highlighting the vertex. So F to E, we added the edge F to E, and E also now is inside S. Next iteration, This time the lightest edge is the 7. But if I select the 7 and highlight it, we will see that there is a cycle here. So we shouldn't do that. So we escape this edge and find the, oh, but it's not the minimum, sorry. It wasn't the minimum. The minimum is the 6. And even if I select the 6, it will make a cycle. So if I select 6, there is a cycle here, so we don't do that. If I select 7, there will be a cycle here. We don't select that 7. So the next minimum can be this 8 or that 8, but none of them make cycles. So once we select this 8, which is a solution, another time the other cell, we have a multiple solution. Now we select this edge and write it down here. Now I have B to E. Edge connecting B to E. And now, sorry, B to D. B to D. That's all. Now all the vertices are here. We have 1, 2, 3, 4, 5, 6, 7, and we have 1, 2, 3, 4, 5, 6, 7 vertices and 7 minus 1 or 6 edges. Now this is the final solution. Now I can duplicate the slide and change this to give the multiple solution. If we want to study the reverse delete algorithm, this time we are going to write all the costs in decreasing order. So we look at the costs on the edges. We can see that the edge connecting B to E, the edge connecting B to E has the cost 10. Then the next maximum is B to C, edge connecting B to C, and that's 9. Next maximum, there's another 9 here, D to F, D to F9. Next maximum, we have these two 8s. We can write A to C, A to C, 8. And B to D, this one, B to D. This one also has weight 8. And then we have this 7, D to E, DE7. And we have the 6, E to G, 6. And this 5 is here, E to F. EF has cost 5. And then we have 4 there, A to B. A, B is 4. We have 2s connecting C to D, CD, 2. And then F to G, again 2. C to F, 1. Now this is the starting point of the reverse delete algorithm. Now we start to, so we duplicate this. In each iteration, we are going to remove one of the edges. How many edges do we have? We had 7 vertices. And now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I need to delete exactly half of them, 6 edges to have 6 remaining edges and 3. So we start from this 10. So we look at this 10. Can I delete this one? Is it going to disconnect the graph? No, we can delete it. And also I delete the cost. So we go to next iteration. I can maybe cross out this one also like this. So this is not existing inside the graph. The next maximum, we have this 9 here, another 9. So let's duplicate and each slide do one of them. So we select this B to C with that 9. If I delete, the graph is still connected. So B to C now does not exist. We removed it. And we go to the next iteration. B to C. Yes. Now let's duplicate. Now the next is D to F. This is also 9. If I delete this, still the graph is connected. Yes, we can delete it. And remove it from here. Next slide. The next maximum is this 8. So I have 2 of them. We can delete one of them, not both. If I delete both, then we are going to have a disconnected graph. Now let's say we are deleting this one for now. And it shows also we'll have multiple solutions. So I deleted A to C. A to C. So deleting this one will not disconnect the graph. So we delete that one. Next one is again 8, but I cannot delete this one. So we skip this and go for the next maximum. D to E. D to E. Yes, we can delete this. D to E. Still the graph is connected. And we cross it out. Next maximum is this 6, E to G. Yes, there's a cycle here. It must be deleted. Or the graph is still connected. And if you look at the graph, there is no cycle there, or we have exactly n-1 edges. Now we are in the minimums. We found the minimum spanning tree. This is the solution. And since we had 2 8s here, each time we can delete one of them and give the multiple solution. So we see another example. But this time we go very fast. We solve with Prim's algorithm first. And we'll see that in this case, the reverse delete algorithm is going to be much efficient because we have 2 or 3 extra edges that we can remove them and find the final solution. Prim's algorithm, initial state we have S empty, all the vertices are inside V minus S. This time the name of the vertices are some numbers 0 to 8. So we have 9 vertices. We are looking for 8 edges to show the minimum spanning tree. Now in the first iteration, we put 0 inside S and we remove it from V minus S. A is the empty set for now. Lightest edge among this crossing edges is this 2 connecting 0 to 3. So 0 to 3 is the lightest. We add that one inside A and we go to the next iteration. Since we added 0 to 3, then 3 will be highlighted and 0 to 3. So we highlighted an edge and a vertex. Now, this time the cut is going to be something like this and similar to a parabola. And the crossing edges are this edge with a cast 4, 1, 6, and 3. The lightest is this one. So this time lightest is 3 to 4. We add 3 to 4 inside A and highlight vertex 4 and the edge 3 to 4. Now the next iteration, we will have a little bit different cut. This time the cut will look like this. So we have some non-selected edges this side and some other side. So we should count all the crossing edges. So we have 1, 2, 3, 4 crossing edges and the lightest is the edge connecting 0 to 1. So the line says 0 to 1. We need to add this 0 to 1 inside A. Now the A is going to be the previous A and this 0 and 1. And we go to next iteration. Now this time again the cut is something like this. As I said, you can draw that. Let me draw that one more time. This shape like this. So I start from here and I go down to somewhere here. Then I want to make a turn here. Then another time I want to make a turn here. I click here. And here I want to make a turn, another click. And when I finish, one more click and I press enter. Then we can change the type to something like this dashed line. This is how to draw the cut in each iteration. Now remove it. So the crossing edges are this edge with the Cij 4, 8, 6, and 4. So we have two of them, we can select one. So we have two. Then at the end of this iteration, we are going to add one of them. So let's see the next iteration. We can select 4 to 8. Sorry, 0 to 8. This one, 0 and 8. Let me select this one. And put that one inside A. So A will change to this one. Now 0 and 8 also is inside A. In the next iteration, this vertex must be highlighted. Yes. Now the cut is only this part. The crossing edges, we have two of them. Lightest is this 4, 1 to 7. Now we add that 1 to 7 to A. So end of each iteration, we show the new or the modified set of vertices. Now next iteration, we have this S034187 remainings or not selected vertices are 2, 5, 6, and crossing edges is this 2 to 7, 2 to 3, lightest is 2 to 7. So we add 2 to 7 to A. So we add this 2 to 7 to A. And go to the next iteration. The next iteration 2 will be highlighted. Now once we have only one crossing edge, for sure we need to select that one. So from now on we can select all the others. So you'll see that we have only one crossing edge that must be selected, only one crossing must be selected, and this is the optimum solution with the minimum weight 25. Then we remove the other non-selected edges. But we can see that we have only two edges, extra edges, so we can delete that one very fast and give the reverse delete algorithm like this. If I want to show the reverse delete algorithm, we will see that we have P and Qs like we have 8, the maximumCijs, and then we have 6, and even I don't need to write the rest because I have 1, 2, we had 9 vertices, we need 8 edges. How many edges do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So since I have 10, I need to delete 2 of them because I need 8. So we can write and see if we need to go forward, then we can bring the name of the other. So what's this 8? 8 is the one connecting 4 to 8. 4 to 8. and the other 8 here connecting 5 to 6, that we cannot remove this one for sure, and that's 6, 3, 2 to 3. So we need one more for sure. After the 6, I have 2 4s. So 2 8s, 1 6, and we have these 2 4s. I can write 0 to 8 with 4, and 1 to 7, again 4. Now let's start to duplicate this and step by step see which one should be removed. And the first, let's say this 4 to 8. 4 to 8. So there's a cycle here, so easily we can see that it can be removed. So we remove this one, 4 to 8. We cross this out and we remove this edge. Next one is 5 to 6. 5 to 6, if I remove this one, then the graph will be disconnected, so we escape this. Next one is this 6, so we can remove this. 2 to 3, so let me cross this one out here and then remove. So 2 to 3, we can remove this one. And then, do we need to edit and delete anything else? No, because we have no cycle and this is the optimum solution. We will solve this problem by solver, and we will see how we can find the same solution by using the adjacency matrix and some constraints based on that to find the edges xij equal to 1, which are going to remain in the tree, and 0 also means that we are going to delete them or remove them from the tree, from the graph, to find the minimum spanning tree.